Now we're going to talk about the chain rule, however, when we have multiple variables instead of just a single variable. So first let's recall what happens when we have one variable and we have a composition of functions. So we saw the chain rule in this case is given by you take the derivative of the outside function, in this case f, leave the inside function plugged in, and then multiply that by the derivative of the inside function. So this is our familiar chain rule. In order to set it up so that this is going to look more like what we're going to come up with multiple variables, let's rewrite this single variable chain rule in a little bit different notation. So let's take that inside function g of t and let's call that s. So now y is equal to f of s, and then s is equal to g of t. So now if we take the derivative of this, the dy dt, we take the derivative of the outside function, and notice that's with respect to s, so dy ds, and then the inside function is ds dt. So we can think of this function here. Remember, when we take this derivative, we take the derivative of f, and then we plug gt in at the end. So that's what's happening here. You're taking the derivative of y with respect to s. So you're just treating this, replace the g of t with an s, take that derivative, and then we'll plug the g of t in at the end of it, just like we normally do with chain rule. And then the outside function here, g prime of t, is just the derivative of s with respect to t. So this is the exact same equation as up here. We're just rewriting it a bit. And this is going to look more analogous to what we're going to come up with for when we have chain rule of multiple variables. So now let's consider the case where we have a function of two variables. So let's let z be f of xy, and we're going to suppose x is a function of t and y is a function of t. So in this case, if we were to plug those in, we would have z is equal to f of g of t and h of t. So in that case, this shows that z here is a function of just t as well. So we can ask, how does z change as t changes? So in that case, we'd be looking for what is dz dt. Notice when we plug in the t, now this is just a function of one variable, just t. So that means we have a regular dz dt. It's not a partial derivative here. It's just a regular derivative because there's only one variable involved once we make this substitution. So to get at this dz dt, we're going to look at an approximation, and we're going to consider delta z and delta t. So back when we looked at linear or tangent line approximations and differentials, recall that we saw that the delta z is approximately dz, which was the partial of z with respect to x times delta x, plus the partial of z with respect to y times delta y. So you can go back and look at that from the section on differentials with multiple variables, and we had this equation here. So we're going to use this because we had if we look at differentials in one variable, we have delta x is approximately dx, and that was dx dt delta t, and delta y was approximately dy, which was dy dt delta t. So we can go ahead and replace that delta x and the delta y in the above equation for delta z, so that we get the t involved now. So if we put these in, notice that now delta z, we have the partial of z with respect to x here, but now I replace this delta x with dx dt delta t to get this here. And similarly, we replace the delta y with dy dt delta t to get this part here. And now we can go ahead and divide both sides by delta t, and we get delta z over delta t is approximately the partial derivative of z with respect to x times the derivative of x with respect to t plus the partial derivative of z with respect to y times the derivative of y with respect to t. And so this is still approximation so far, but now if we let the delta t go to 0 in this approximation, the left-hand side will become dz dt, so we'll get this equation here that says dz dt is the partial of z with respect to x times dx dt plus the partial of z with respect to y times dy dt. So this is how we would go ahead and calculate the derivative of z with respect to t if we have these functions that are a composition where z is a function of x and y, and x and y are both functions of t. So there's a nice visual way to represent this that helps us to keep everything in mind. So we start here with our outermost variable z. And then we saw z depends on x and z depends on y. So on the layer below that, we write an x and a y, and we put those arrows going from z to y because it depends on x and y. And now we saw x and y each only depend on t, so we write a t in the layer below that, and we draw an arrow from x to t and y to t to indicate that dependence there. And now we're going to go ahead and fill in next to these arrows. So notice in the layer below z there are two variables. So on the direction going down from z to x, we want the derivative of z with respect to x. But since there's two variables on this row below it, it needs to be a partial derivative. So we get a partial derivative of z with respect to x. And similarly, if we go down towards y, there's two variables on this row here. So the derivative of z with respect to y needs to be a partial derivative of z with respect to y. And now going from the second row to the third row here, there's only one variable in the bottom row here. So that means the derivative of x with respect to t is just a regular dx dt, because x is only depending upon one variable. And similarly, y only depends upon one variable, so you get a dy dt. And now how do we get our formula that we had on the last slide from this? So to get dz dt, we follow all paths from z down to t. So we go this direction and this direction. So we take this term here and multiply it by this term. And then we add it to all the other directions. So then we can go this direction as well. So we do dz dy and then dy dt. So we see this is how we can remember this formula. You just start at the top with z, and you go this path down here. That gives you this one. If you go this path here, that gets you this one. And no matter how many different variables you put in here, you can also add several more variables to the second row, and you just get more terms because you just have more paths going from z to t. So it's pretty easy to remember this now if you just draw this picture out and fill in, and just remembering that if there's more than one variable, the derivatives are partial derivatives. If there's only one variable, then they're regular derivatives. So let's go ahead and see an example of this. So let's let z equals f of xy be x times sine of y, and x is going to be t squared, and y is going to be 2t plus 1. So we can calculate all of these derivatives we need. So the partial of z with respect to x, this will just become a 1, so I just get a sine of y. And then since in the end I'm going to want everything to be in terms of t, we'll just go ahead and replace that y with a 2t plus 1 here. If I take the derivative of this with respect to y, the x is a constant, so sine of y becomes cosine of y. So I get x cosine of y. Now I'm going to go ahead and replace my x with the t squared and my y with the 2t plus 1. And I also need dx dt, so derivative of dx x with respect to t is just 2t. dy with respect to t is just 2. So we've calculated all of the pieces we need for this partial derivative, or this derivative of z with respect to t now. So we just put those together. So we have dx dt times delta z delta x here, and so we get 2t times sine of 2t plus 1, so that's this term coming from the x direction of the diagram. And now if we go down the right side of the diagram, we get the 2 times t squared cosine of 2t, so 2t squared cosine of 2t plus 1. Okay, so you just follow those diagrams down and you calculate all of the, so when we look back at this diagram, we calculate each piece here, which is what we did, and then we put them all together to get this formula here. So this is calculating those pieces along the diamond, and then this is putting them all together by going down the different paths. So of course we don't want to restrict to forcing our x and our y to be functions of only one variable. Obviously our functions can have lots of variables involved. So let's look at one more example of this, and then from this we'll be able to extract, no matter how many variables, we'll be able to figure out how to do chain rule, even if there's lots and lots of variables. So let's suppose we have z is equal to f of xy again, but now let's let x depend upon u and v, and y depend upon u and v. So now we don't just have one variable at the bottom, we're going to have u and v at the bottom. So if we put this into a diagram, we start here at the top with z, and then z depends on x and y, so we go one below that and we put x and y. And then the x and the y each depend on u and v, so the bottom row has u and v in it. And now if I want to take partial derivatives, or if I want to take derivatives, I have to follow all of these paths. So if I want the derivative of z with respect to u, I have to go this way, and then I have to go this way and this way. And now notice to label these arrows, there's two variables below z, so both of these have to be partial derivatives. And now if I go to the second row, The third row also has two variables, so these have to all be partial derivatives as well. And you can see if you had 10 variables here and 20 variables down here, you'd still just be doing arrows, and the diagram would become a giant mess, but you could still just fill the diagram in like we've done here. It'd just be messier, and we could still figure out the chain rule from that. So let's see how we get the chain rule off of this diagram then. So if I want delta z delta u, so notice that it has to be, since there's two variables down here at the bottom, it has to be a partial derivative because z is depending upon u and v. So I go down this direction, delta z delta x, and then delta x delta u, so that's this term here. And then I go down this direction, so delta z delta y, and then I have to take this path to get to u, so I get a delta y delta u. And then for v is the same thing, so now I'm going to go x to v to get this term here, and I'm going to go y to v to get this term here. So there's no need to memorize all of these different formulas. You can, as long as you understand how to draw this picture and how to work the picture to go in the different directions, you can recover any chain rule you'd like. So let's see one example to finish this up in this setting. So let's let z be x e to the y, x be u squared plus v squared, and y be u squared minus v squared. And let's compute delta z delta u. Right, so we're going to do delta z in this direction and in this direction. And we're going to completely ignore the v, other than the fact that since it's there, it makes everything partial derivatives. So we do all of our calculations here. We take the derivative of z with respect to x, and we're just going to get ey, and we go ahead and replace that in there. If we take it with respect to y, we just get x e to the y, and then replace the x and the y. Derivative of x with respect to u is 2u. Derivative of y with respect to u is 2u. So if we put all this together, it's delta z delta x times delta x delta u. That gives me this term here. And then it's delta z delta y times delta y delta u, which gives me this term here. So once you understand how to do the diagrams and you understand how to take partial derivatives, chain rule in multiple variables really isn't any more complicated than chain rule with a single variable. You just have to follow the different paths and understand how to get those.